Welcome to classes on organic chemistry. It is the class number 15 and it is the continuation of class number 14, and the topic was general organic chemistry, and I was discussing about the different optical isomers, and already the constitutional and configuration isomers. Out of this I have discussed geometrical isomers in the last class, and today I will explain optical isomer, and this isomer is of configuration isomers. So this optical isomer is of utmost important for your class as well as any type of entrance exam point of view. So you minutely follow the class so that you can do a lot of things with the concept which you can learn from the classes. So first of all, before coming to optical isomerism, I will just explain one term first. So it is a term you will get in physics in well-defined manner. Till I will try to explain plane polarized light, because this point will come over and over again. So natural or normal light or sunlight have vibration all through the different axes, and if this normal light is passed through nickel prism or calcites or some type of crystal, then these lights now aligned in such a way they remain in the same plane. So that light is called plane polarized light. This is often used in explanation. So this is plane polarized light. So keep it in your mind, this point. So there are some objects of the molecules in chemistry. We will be concerned with the molecules in organic chemistry which has the ability to rotate the plane polarized light. That already I have defined, not normal or ordinary light. It is not ordinary light, it is plane polarized light in one axis. Vibration waves are in one axis. So objects of molecule which has the ability to rotate the plane polarized light either towards right or towards left are called optically active, and the property by virtue of which it can rotate the light is called optical activity. Am I right? So some organic compound has the ability to rotate the light towards right, and some has the ability to rotate the light towards left, and this property is called optical activity. Next, another important term you need to know before coming to main point of the chapter: racemic mixture. And this point beforehand I am telling you will come in need in second year haloalkane haloalane chapter, and it is one of the important property of SN1 mechanism. So you will get the term racemic mixture. If you can now understand what is racemic mixture, you can understand the topic. Again, in the next topic, in next part, bit by bit, we will interact with the same things, racemic mixture. So beforehand I am explaining this: the equimolar mixture of such compound, the compound which we have already explained, that has the ability to rotate light in the right direction, another type compound which has the ability to rotate light in the left direction. If these two types of compound is present in the reaction mixture in equimolar proportion, one organic compound has the ability to rotate the light towards right, and other compound has the ability to rotate the light towards left, and these are equimolar in the reaction mixture as product, that finally this solution is optically inactive due to external rotation, external compensation, because the one compound has the ability to rotate light either right or left, say 50 degree. So other compound will rotate the same light at the same extent 50 degree to the opposite direction of the first compound. So finally this 50 and 51 is plus, other is minus. Finally it will give you a mixture of product which is optically inactive, and this optically inactivity is due to the different rotation of different compound, hence it is called externally compensated. This is optically inactive due to external compensation, means externally compensated. Externally, one is rotating right, other is rotating left at the same extent which has rotated right to the left. Am I right? So this type of mixture is called racemic mixture. Another important point is meso compound, and very often from this point in entrance exam question is asked. Meso compound. So meso compound is another. Mind that meso compound actually it was one of the isomers of the optically active compounds. So optically active compound which becomes optically inactive due to the presence of plane of symmetry. Later on I am coming what is symmetry. Plane of symmetry is called meso compound. This is inactive due to internal compensation. Means, say I have taken an example of tartaric acid. The structure is this. We can change the structure. O is left, R is right. Here that carbon OH is left, R is right. So, or we can fix it, we can change it, or we can fix it, we can change this. Am I right? A lot of structure of tartaric acid may be drawn. Am I right? Out of this, I have chosen this to explain the term meso compound, because if this compound is actually two chiral center, optically activity is there, but due to presence of plane of symmetry, in short I am telling it is a line or axis. If it is drawn through the compound, and after breaking the compounds into two equal halves, one half exactly fit over the other, if in such a way a line is drawn, then that compound is meso. It will not be optically active, it will be optically inactive, because if these parts rotate light towards left, at the extent this part again will rotate the light towards right. So due to this internal rotation, one is compensated, the action of one is compensated by the action of the other in opposite direction, hence it is internally compensated in the same compound. So that's why this compound is optically inactive. Mind that another structure of this compound is, keeping this is fixed, you change OH here, H is here, that time it will be optically active, because in this point you can't draw a line which can make this or divide this structure into equally two halves, so that one half exactly fit over the other. Again we can make fixed second one, and you can change OH and H here, again that compound will also be optically active. Other form of tartaric acid is optically active, except this form is optically inactive, and this form is called mesoform only because a line which can be drawn so that it is divided into two equal parts, one part exactly fits over the other, and that is called plane of symmetry. So optically active compound which has a plane of symmetry is exactly optically inactive. Always in the entrance exam option is given which part of the tartaric, which structure of the tartaric acid is optically inactive. So you can find out in this way. Which we will often come in across while we are discussing the topic. We are coming to the main part, when we can tell that this compound is optically active or not. So what are the criteria of optically activity? Besides a lot of points, just I will point out one of the two important striking points upon which you can very easily understand that whether a compound is optically active or not, if it is supplied or if the question is asked in the exam. So one of the important criteria is the chirality, and other is the carbon which is chiral. If it is chiral, I am coming what is chirality. If it is chiral, then that carbon which should be sp3. So two conditions you should keep it in mind, that carbon which is the compound which having carbon, that carbon should be a chiral carbon, or that chiral carbon is also called disymmetric carbon. So if the carbon which is optic compound which is optically optically active must be a chiral center, a carbon, and this carbon must be disymmetric. So chirality, disymmetric are the same thing. I am going to explain a bit later on. And if this is chiral, I will explain. Then this carbon, chiral carbon, should be sp3. It should not be sp2 or it should not be sp. It should only be sp3. If these conditions are fulfilled, then this organic compound is optically active. Now let us explain what is chirality. So the main important criteria of compound to be an active one is that the compound should be a chiral one, or compound must be a disymmetric one. Now let us explain what is a chiral or chirality and what is dissymmetry. So this point again you should know what this point is. So what I have written here is a molecule is said to be chiral if it doesn't contain an element of symmetry. So you must know what is symmetry and what is elements of symmetry. Again I am coming. So first of all, from the definition it is clear to us that a molecule is said to be chiral if it doesn't contain an element of symmetry. Molecule should not contain element of symmetry, and the mirror image are non-superimposable, and this property of non-superimposability of the mirror image is called symmetry or chirality. And the compound which, if we find a chiral, means if it doesn't have an element of symmetry, and if you take the object and image of the mirror image, object and image with the help of a mirror, then object and image are not superimposable over other. So two condition: the compound should not contain element of symmetry, I will explain. And if this compound having no element of symmetry, if this has object and image relations and object and image should not be superimposed over each other, then this property is called chirality and dissymmetry, and this compound is nothing but optically active. Just I am taking you another example. See, say this is P. Now if you draw this figure, if you put a mirror over there, then P becomes this. Now this is object and this is image. So object and image cannot fit over other. That is called non-superimposability. Simply two hands. One hand is the object and this hand is the image of this object. So if you put this one, so one over the other, it is not exactly placed over each other. So if the object image relation does not fit or place exactly over other, this is called non-superimposability. Otherwise, if you see, if I draw M and if I place a mirror, the structure of M again will be M. So M will exactly fit upon this. This will be superimposable. And if it does not fit, then it is called non-superimposability. So first point, a chiral atom, a chiral compound must not have element of symmetry, and if this compound doesn't have element of symmetry, if it has object and image distances, then object and image is non-superimposable over the other. Such type of criteria is called chirality or dissymmetry, and this compound is optically active. Let me take one example. Say you have this compound. Now if you take the mirror image of this one, you will get the change of this one. This will come here and this will go over there. Am I right? This is the change of the mirror image, and these two will remain same. So now you can't place over this one exactly, these two are mirror image. Now this compound is called chiral because it does not have any element of symmetry, and this is chiral carbon. Now second point is that I have effaced out. Second point is that carbon should be sp3. Now you count the hybridization of this one. One is its image is not superimposable over the other, and second one, this carbon is sp3. If the carbon which we concerned whether it is chiral or not, if it has double bond in the structure or triple bond in the structure, then blindly you will tell it is not an optically active compound, because whenever you introduce double bond and triple bond, hybridization of carbon will not be sp3, it will be sp2 or sp. Am I right? So only criteria for the optically activity is that the carbon or cryogenic center, stereogenic center or chiral center must contain all single bond and it is sp3 hybridized. So this molecule will be optically active. Now element of symmetry. In my definition, I have told the elements which does not have element of symmetry and that object and image are non-superimposables are called chirality or dissymmetric. Now what is elements of symmetry? Element of symmetry are of three types: plane of symmetry, for entrance point of view, these points are to be known, and for those who are the class, they will just simple pass out, will try to pass out from or will get promotion for 5 year and second year. They need not to learn these things. This is important for the entrance point of view: plane of symmetry and center of symmetry and alternate axis of symmetry. But for all, plane of symmetry is important. What is plane of symmetry? A bit earlier I have told you COOH. I gave you the structure of tartaric acid like this. If you recall, you will get this, that this is the form of tartaric acid where this compound has been divided exactly into two equal halves. One half is exactly fit over the other, and this line or plane is called plane of symmetry. Due to presence of this, the compound will not be optically active, though there is two chiral center. So this is called plane of symmetry. This is called plane of symmetry. Now what is center of symmetry? So it is a bit difficult things, but you just for your knowledge, I am telling you that I have drawn the structure of the compound, where I have drawn in center of symmetry. This is center of symmetry, center of symmetry. If you draw a line over two opposite corner of this two group, CO and CO, or NH2 and NH2, and if you extend the line, upon extension of line, you will get the similar things are attached, CH3, CH3. From the center, if you extend, if you join these two, am I right? And if you extend the line, again you are getting H and H. On extending the central point towards the opposite diagonal, you will find the same group or atoms are being attached. That point is called center of symmetry. If a compound having center of symmetry, then though the compound is a symmetric one, having different groups or atoms is attached to this carbon, yet it is not optically active. So I have explained two things. One is center of symmetry, other is plane of symmetry. Now alternate axis of symmetry is a bit hard and not to learn, and it will take time and it will not be any use for your knowledge. That's why I am skipping off this thing. Now I have taken one example of optically active compound where I have drawn CCH3OH and COOH. It is nothing but a lactic acid. Now I have shown you that carbon is a chiral carbon. The carbon which has different atoms or group attached with it are called chiral carbon. It has 4 different group are attached, then it is optically active. So it is chiral carbon. It has no plane of symmetry. You can no way separate into two form. It doesn't have any center plane of symmetry, does not have alternate axis of symmetry, does not have any element of symmetry. So it is non-superimposable. It is sp3 hybridized. All these factors give rise that this is an optically active compound. The carbon has different atoms or group attached, and it has no plane of symmetry, means you can't separate into two equal halves. It doesn't have any point of symmetry, center of symmetry, does not have an alternate axis of symmetry. It is sp3 hybridized. All these points give rise to conclusion that you may conclude that this is nothing but an optically active compound. Now again, very important point of this chapter is the nomenclature of optically active compounds. If you have got that these compounds are optically active, how you can name this compound, and very often these 3 types of notations are asked in entrance exams, also in your class exam. Mindfully follow. There are DL notation or DL system. One is retro and trio system, or other is RS configuration. RS configuration very often asks which has given this configuration. The name of the person or a chemist who has given this configuration is Khan in Golden Prelog. They have given the structures RS and configuration. S configuration. R means rectus, means right, and S means sinister, means left. Am I right? Later on I am coming. So first of all, I am coming to the type DL notation, and very important part of this chapter is this part, DL notation. Minutely follow. It is not hard, it is very simple. And again, this part you will get in higher secondary second year. This part yes, this type DL system is very often used in polyhydroxy compound or sugar chemistry involved. Get in biomolecules in second year, you will get D-glucose, D-fructose, L-glucose, L-fructose. Then you will be confused with this term. So beforehand you should know how you have got this DL notation. This is called D system and this is called L system. And how it has come from? It is a relative system. It is not absolute. System is relative. That is, with relation to the other structure, the structure of other salts are derived. If this salt is D salt, D glucose or L glucose, that can be termed with the help of this figure. And since the structure of sugars or polyhydroxy compounds are derived with the help of these two fixed structures, and in relative to these structures their name is given. Hence DL system is a relative structure. So if the sugar, say C6H12O6 glucose, if the structure, if you go to the last part, if you get OH and OH are on the same side, then this structure is called D-glucose. And in the glucose structure, if you find that last two carbon where OH are in the different phase, then you will tell it L structure. I am giving you one example. Say in this hand it is blank. If you give CH, and if it is H, and if it is, this is same as D structure, is this part is same with this. Am I right? So I will give it D, and I have given here CH2 means D-glyceraldehyde. Name it D-glyceraldehyde. And again, if I write this one CH2 here, it will be L-glyceraldehyde. So D-glyceraldehyde, D-glucose, L-glyceraldehyde, L-glucose. The name has been derived with the system CH2OH and COH. If they are on the same side, they are D. If they are on opposite side, they are L. Hence, it is relative structures. Next systems of giving the nomenclature of actively active compounds are the erythro and thrio, and these two structures, the main condition is that there should be number one, there should be two chirogenic center, there should be two chiral center of carbon, means there should be two carbon having four different groups. This optically active center are two, this carbon, because this carbon has chlorine, CH3H and whole group. So four groups are different. This carbon, this bromine, C6H5H and whole this group. So these two carbons are attached with four different groups of atoms. So it has two chiral centers. So first condition, erythro and thrio systems should be nomenclatured with the in the compound which have two chiral centers. Am I right? And this carbon should be AB and carbon should be BC. Means in carbon which should be attached with AB, means one or more two same groups should be attached. At least two same groups should be attached. If these two carbon attached should be attached with the two same groups, and this are different, and one R is R and other R is R dash. If these two carbon have at least two same groups and that alkyl and this part are different, then we can designate name by erythro and thrio. Now the same process is why it is called erythro, because this same priority group, chlorine and bromine, higher atomic number groups are on the same side, that is called erythro, and this higher atomic number or priority numbers are in opposite direction, which is called thrio. Nothing else, nothing more different, more special things is attached with this explanation. This is the sufficient regarding erythro and thrio. Now the most and the last part of today's lecture is again very important, which is RNS configuration. R means rector, S means sinister. Khan Prelog and Ingold has given this notation, and this RS configuration is absolute. Mind that it is absolute, because it is not relative to any other. It itself has given rise the structure. R for rectus means right, S for sinister means left, means the structure which is designated as R, that has the ability to rotate the plane polarized light towards right, and the structure which will be designated as S, this structure of the compound will have the ability to rotate the light in the left. Am I right? So earlier we have presumably told that some compound has the ability to rotate that towards right and some has the ability to rotate that towards left. So the compound, now we will designate which compound has the ability to rotate light towards right and which has the ability to rotate the light towards left, and we will designate it as well by R and S configuration. And this configuration again is based on the priority. So minutely follow. The first one is this is the very important. Very often you will find problem in giving RNS notation. So minutely follow, and this is the last part, and minutely follow you will be benefited a lot. Say the chiral carbon C has three different group, chlorine, bromine, iodine and H. Here in terms of priority order, atomic number of the iodine is highest, this is second, this is third, and this is fifth. The priority order is in terms of atomic number is like this. This is the priority order. Am I right? So this is 1, this is 2, and this is 3, and this is 4. So priority order bottom means the in the priority which atom or group is at the bottom, so you need not to do anything. You need not to do anything. The priority order group or atom is at the bottom. If it is at the bottom, just you see how it rotates. 1 2 3, it the movement is like this. Am I right? So it is S. So this compound will rotate the light towards the left, so it is S configuration. It is S configuration. Mind that if the priority group is the bottom, no need to do in terms of priority, place 1 to 3 and see the rotation. It is clockwise or anti-clockwise. If it is clockwise, it is R. If it is anti-clockwise, it is S. It is anti-clockwise when H is bottom. Second condition, you see, in terms of priority, the nitrogen is the highest atomic number. Second is CH3, CH2. This is CH3, this is C, and here it is actually CH3, CH2. Am I right? So first C and that C is comparables, atomic number 6 6, and next is hydrogen, but here next is carbon, so it has got more priority order. Am I right? So C2H5 is next and C3H3 is the least. So what happened here? It is 1, it is 2, it is 3, and it is 4. Our target that the least priority groups or atoms should be at the bottom, always at the bottom. At the earlier case it was bottom, so we need not do anything. We needed to do anything. Here we should do something. What will do? If it is in the top, we need to bring it at the bottom, so we will make the rotation 180 degree. So if we make the rotation 180 degree, so what will happen? That ammonia NH2 will go up and H will go here. So if it rotates in this way 180, so that will also rotate. So CH3 will come and C2H5 will go there. If you rotate it top to bottom, if it comes here, if it goes there, means you make the rotation 180. So along with the 180, this is 90 and this is 180. Along with this rotation, this will come here and this will go there. So we are getting this. So this is 1, this is 2, and this is 3. So your rotation is in clockwise direction. It is R configuration. So we'll give its configuration is R. Am I right? So third one is mind that where least priority is the left. Least priority again, this is 1, this is 2, this is 3 in terms of priority. Yeah, least priority is the here. So in this case, what we'll do, we'll be concerned that we should keep the least priority to the bottom. So to make it to the bottom, that should be here. Mind that NH2 will be fixed. NH2 fixed. We need not do anything. We'll be concerned with this. Am I right? So when we'll keep hydrogen here, COOH will go here and that will go over there. No change. You mind that you don't keep it same side. We need to bring here this. When we will bring it here, that place is vacant. It is fixed. It is fixed. When we will keep it here, that place is vacant. So instantly this will come to its place and this will go to its vacant place. When this will come, when we will move hydrogen here, this is vacant. Then in vacant place CH3 will come. Then this will be vacant. In this vacant place CW will go. So when we will move hydrogen here, this will come over and this will come there. Now you see what happened. Now you see this is 1, this is 2, this is 3. Again you are getting this. You have got R configuration. So case number 3 is over. Now the least and last case is case number 4, where the least priority order is at the right. Least priority group or atom in the right. So what will you do? Again we will keep fixed. OH fixed. OL fixed. will concern with this is 1, this is 2, this is 3. Am I right in terms of priority, atomic number? Now, what will do here? We will concerned with this hydrogen. Am I right? So, when we will move this, it is fixed. OH is fixed. OH is fixed. When we move this here, hydrogen here, so that place is vacant. So, this will move to that vacant place. When this will move to that vacant place, it is vacant. So, that will replace its vacant place. So, what we get here is configuration means clockwise direction. Now I am giving you last example where you will find in very often AI, EEE, JEE, all types of entrance, staff entrance exam, these questions are very often asked. In the exam, you are given, give the RS notation to carbon 2 and carbon 3. These two are chiral centers. These two chiral centers, what is it is R, it is S. What is the rotation type? Rotation in carbon 2 and carbon 3. With respect to position carbon 2 and carbon 3, you are asked to give the RS notation. Now you see, a bit difficulties is there, but you can do it very easily. Say, if you take 3, in terms of 3, what will you do here? 3 carbon is this, OH is here and CH3 is here, hydrogen is here. Am I right? Now 3 is over. Now above this, a lots of things. You write CH, OH, CH3. So you have got 4 hand, 1, 2, 3, 4. You see 4 hand are different. So it is chiral, it is optically active. Am I right? Now you see, you need to designate it RNS. So you see, at the very first point of this designation, I told, if the least priority order is the last, you need not to do anything. So least priority is hydrogen. So hydrogen is the last, you need not do anything. So at atomic number, OH is the more priority, then CH, OH, CH3, then CH3. Why? Because O atomic number is 8, carbon is 6. Now carbon 6, here carbon 6. Here second group is hydrogen, but here second group is OH or second group is C. So in terms of when first group is the same, go to second group. You see atomic number. If atomic number is second group is high, then it's higher priority. So priority of this group is higher. So you have got this is 1 and this is 2 and this is 3. So the movement is anti-clockwise direction. So you have got what? 3 is S. Am I right? Now come over this 2, carbon 2. So you draw carbon 2, H, CH. It is this part, OH, H, CH3. And lower part again is CH, OH, CH3. I have concised it. I have condensed it in this form. So now again see this carbon is chiral carbon because 4 groups are different, atoms of groups are different, and C is in sp3 hybridized. Now you see how we will do this. Now in the third rule, I have told you least priority hydrogen should come to the bottom. So what will you do here is this will remain same. We will do what? That hydrogen will come over this. It should come bottom, least 1 bottom. This is least. Am I right? 1, 2, 3, and this is least 4. Least. So when this will come over there, that place of hydrogen is vacant. So OH will fill this vacant. Am I right? Now when OH will fill this vacant, this place is vacant. This place will be filled by this group. Am I right? This is third rule I gave you first. So what you see here is, say O priority order 1, this is 2 and this is 3. Your movement is in this direction, again in anti-clockwise direction. So with respect of carbon 2, it is 2A. So whole configuration is 3S, 2S. So this is all about regarding designation of 3S configuration, what is absolute configuration. Hope you have understood the class and minutely followed the class. Thanks a lot for watching the class.